Nowadays, all of you know, so it's very well recognized that wastewater treatment plants are not efficient in the removal of contaminants, contaminants that are called or known as contaminant of emerging concerns. So, large amount of these contaminants are present in the effluent. So it is mandatory develop the point. Doesn't work. Oh, okay. Sorry. Develop tertiary treatments able to remove these contaminants in order to get high quality effluents, water of high quality for water consume, to prevent contamination of environmental waters, and also, especially we are going to use this effluent for use, especially in the irrigation practice, for example. So in this axillary advanced oxidation processes play a very important role because they are very efficient in the elimination of these contaminants. But these treatment processes are usually evaluated in order to confirm that they comply with the our expectative. So we usually study or monitor the mineralization degree by conventional techniques. Also, it's important to evaluate the micropollutants removal, identification contaminants of emerging concerns, and also transformation products that can be formed during the treatments. With the same chromatographic techniques coupled to mass spectrometry are the main option. And also it's important to evaluate disinfection by other analytical or microbiological analysis. We are going to focus in this aspect, in the evaluation of the contaminants and transformation products in the water. Difficulties of the analysis are very well known. We need to identify a high number of compounds. Think that there are registered more than 100,000 compounds, chemicals, and only in normal network web page you can find a list of more than 1,000 emerging substances of concern. And this is only a part of the problem, because still there are a lot of compounds that are unknown, especially we think in the transformation product that can be generated in the media or also during the process, the wastewater treatments. Another difficulties are associated with the different chemical physical properties of the compounds that difficult the selection of analytical methodology for their analysis, and also the low concentration. They are present at very, very low concentration, nanograms or micrograms per liter, and also they are present in very complex matrices. So the analysis of minor compounds in a complex matrix with major compounds present at higher concentration is quite difficult. So we need analytical techniques with high sensitivity and high selectivity to solve this problem. The first step in the analysis is the sample preparation. So normally, because of the low concentration of these compounds, pre-concentration steps are necessary. In this case, solid phase extraction is widely applied, using, for example, Oasis ALCB adsorbent. And finally, we start with a volume of hundreds mils of wastewater, and finally we can obtain 1 ml, so a pre-concentration of the compounds in the samples is obtained, and also is useful for the removal of interferences. But another option, each time more and more applied is the direct analysis of the samples. Avoiding the sample preparation step, is possible to inject the sample directly only by filtration and adding a little bit of organic solvent. And this technique is very simple, cheap, no organic solvents are used, and the analysis is far faster, and the detection limits are quite low, especially when you are using a new instrument, because new analytical instruments are very sensitive, so it's possible to apply this strategy with good results. Advantage, all of this, and also but the disadvantage is that also another important is that you avoid also the losses in the extraction methodology. But of course, compounds present at lower, very low concentration maybe escape of the analysis. So, but it is useful because more of the contaminants present at higher concentration, the more important compounds can be efficiently and very fast, in a very fast way, determined. Thinking in the analysis, in the determination, we can choose different analytical techniques, always based in the couple between gas and liquid chromatography and mass spectrometry. But the selection of the adequate technique is based in the objective of the analysis. We can focus our objectives in the target analysis, that means identification of contaminants of emerging concerns. In this case, a selected group of compounds well characterized by reference standards are selected, and the method I've developed for usually for quantitative purpose. The problem is that only a limited number of compounds, known compounds, can be evaluated with this technique. In the opposite, non-target analysis is more intended for the identification of unknown compounds, like transformation products. Compounds unexpected or unknown are identified without reference standards, are not available in most of the cases. So we need to evaluate an unlimited number of analytes with high sensitivity. So techniques working in full scan mode are required. And analytical technique also with capabilities, or identification capabilities. With respect to target analysis, is the analytical strategy more frequently applied in wastewater treatment process? When we use it, when we want to characterize the effluent or the wastewater that we want to treat, so also for evaluation of the effectiveness of the treatments, is also useful for design of and optimization of the treatment processes. For comparison of different treatments based on the focus in the removal of contaminants, and also to assess the quality of the water. Okay, how can I do it? Can I do it? Using instrument, normally liquid chromatography is the preferred technique, because the wider scope of the analysis is able to analyze compounds with higher polarity than gas chromatography, and normally coupled to hybrid, triple, quadruple, or similar analyzers. Why? Because this technique has high selectivity, so it's able to remove or evaluate the compounds with less in matrix interferences. Also, the limit of quantification are very low with this technique, and a reliable identification is also possible with MRM methodology. And the quantification performance is quite good in terms of linear range, accuracy, reproducibility, etc. This is an example of target analysis. We have first select which compound we are going to analyze, and we have the standard, so we characterize the standard with the retention time in the chromatography, in the chromatogram. We select two transitions that mean two masses, product ions, characteristics of the compounds, and also they must be present at a correct ratio. When we analyze the sample, we check that all these identification criteria are fulfilled, and then the identification is obtained. And then the first transition, which is the more abundant one, is used for quantification purposes. This is an example of the application of this technique in a wastewater sample. Here we can see the chromatogram before and after the application of a photophantom treatment of this water. You can see easily that the treatment is efficient because most of the peaks that correspond to compounds are reduced or eliminated. Even we can evaluate compound by compound the removal rate of the compounds. Okay. Also, this technique is interesting when you want to compare different treatments. In this case, the comparison between solar photophantom and oxygenation was evaluated when they were applied to a wastewater effluent, and the treatment were optimized to get 90%, more than 90% of removal of the contaminants. So comparing, in this case, for example, the time of treatment, the treatment times is more fast, and the same objective is obtaining with less reaction times in the case of solar photophantom. So this is comparing the focus in an objective of removal. It's easy to compare the efficiency of different techniques. But in addition to this technique, target analysis technique, the increased availability of the high-resolution mass spectrometry have improved the identification of compounds, especially not only target compounds, but also non-target, as, for example, the transformation products. Why? Because high-resolution mass spectrometry provide very high sensitivity in full scan mode. That means that all compounds present in the sample can be determined simultaneously with a complex and time-consuming method development. Also, we obtain a high resolution and high selectivity, so it's possible to the differentiation of isobaric compounds. Also, a molecular formula can be assigned to parent and fragment ions based on the accurate mass measurements. And finally, if you use hybrid system, you can also combine mass spectrometry with MS spectrometry, and then increased structural information can be provided for the identification of the compounds. In order to have an idea for those not familiar with this concept, when we speak about accurate mass, we are speaking of the measure of the mass, molecular mass, with a lot of decimals, with a high exactitude. So, for example, these three compounds, if we use nominal molecular mass, we can disguise them. But if we use the accurate mass of the elements, it's possible to obtain the accurate mass of the molecular mass with more accuracy, and then it's possible to differentiate these compounds based on the mass. These techniques can be also improve the identification capability in target analysis. For example, an analytical strategy applied is the first step is to select the compounds that we want to analyze and prepare a list including information about the formula, mass, extraction mass, and also, if it is target analysis, we include the retention time of the compounds. Then, when the analysis finishes, this list is, the compounds in the list are searched in the chromatogram, and when a positive finding is found, we check that this mass is not present in the control sample, in a blank sample, so we are sure that comes from our samples. And when the compound is detected, a mass spectrum is also acquired. So the identification criteria in this time is the mass error between the theoretical and experimental mass of the compound identified. Also, we check the isotopic pattern. And the MS spectrum can be searched in database, and we can obtain a confirmation by a comparison between the experimental spectrum and those stored in the database. So the identification is widely improved with respect to target analysis. Sorry. Target analysis with conventional triple quadruple priming. But maybe the most important capability is the analysis of non-target compounds, especially the identification of transformation products. You know that sometimes these compounds are generated during the processes and sometimes are more persistent and more toxic than the parent compounds. This is an example. Here we see for AA, it's a metabolite of dipiron. We studied the photolysis of these compounds. The initial solution was not toxic, applying an acute toxicity test with Agüera magna. But after the experiment, when the parent compounds had disappeared, the toxicity had been increased. So this is probably because of the presence of transformation products. Here, we did a study identifying different structures corresponding to these transformation products, and 3 of them were identified as more persistent than the parent compounds. Here we can see the time evolution of these compounds, and one of these was identified as toxic, probably the responsible of the increase in toxicity. Probably this compound or the combination of this compound with other transformation products that are also generated. This is another very known example, the formation of dioxins by the photolysis of trichosan, which is an antibacterial and fungicidal agent, very widely used even in toothpaste. But this is, in order to identify this transformation product, there is an interesting strategy applied with high resolution mass spectrometry. It is known as suspect screening or suspect analysis. The strategy is very similar than those applied in the identification of target compounds, but in this case, in the suspect list include not the list that we prepared initially include compounds that are not available available in our laboratory. This technique is useful for a wider to expand the scope of the analysis to compounds that are not available in our lab. So we don't have the possibility to analyze it by target techniques. Then the list we prepare is search in the chromatograms. We find positive and apply confirmation, the same confirmation criteria previously comment. And finally, when a list of positive findings are found, they are confirmed by the MSMS spectrum of the compounds. The final confirmation is only possible by the purchase of the commercial standard and the analysis confirming the retention time, of course. This is an example when in a work performed in our group where a list of 1,300 compounds was monitored. The extraction, the peaks extracted in the first step were 690, long list of tentative positive, but after application of the confirmation criteria and comparing the mass spectrum of this positive with the commercial database, we could reduce the list to only 32 compounds. We purchased a standard and 28 were finally confirmed. So it's an interesting strategy to identify compounds, but it's time-consuming and it's not easy to evaluate it. So a little bit, please. Sorry. This is an example of the identification of methadone. This is the strategy. Apply the mass spectrum. The mass spectrum confirm the mass, the molecular mass of methadone with a very low error. The MS spectrum was positively identified in a database, and finally we could also the structure with the assignation of two relevant fragment ions. So after the acquisition of the standard, we could confirm that it was this compound. The same strategy can be applied for the identification of TPs. In this case, we can select a list including TPs previously reported in literature, and also we can use prediction software, pathway prediction software tools to propose structure that can be originated by transformation processes. This is an example of how the EVAG pathway prediction system software propose different structures that can proceed by the degradation of metabolisms of neuron. This we introduce in our suspect list the masses of this structure, and we can use this list to identify this transformation product. So when a compound is identified, tentatively identified by this procedure, if the compound is previously reported in literature, we can confirm the positive identification by comparing the our spectra with those reported in literature. Also, but not always is possible to use this information, and when it's not available, we need to propose extractors by structural elucidation of the mass fragments. So finally, you can find in literature a lot of papers, a lot of articles, including the identification of this transformation product of different compounds. So as a conclusion, we can say that there are powerful analytical tools available for the analysis of contaminants, useful for evaluating their behavior during wastewater treatment and their impact in the environment. Triple quadruple or similar analyzer provides high sensitivity and good performance in quantitative analysis for target analytes, and high resolution mass spectrometry coupled to liquid chromatography open the possibility of expand analytical methods and also identify unknown compounds. And finally, we had to say that new developments in method development and in software to manage the information generated by these techniques, improving this procedure must be developed.